Hello and welcome to Answering ATPL. This video is the third video of a three-part series concerning the topic of direction. The first video discusses the basic of direction. The second video explains the components of direction, and in this video we will discuss grid direction, or sometimes referred as grid navigation. Section 1. Why do we need grid direction? The simple answer is economy and necessity. By this stage of your learning, you should already know that grid circle track is shorter compared to ram line track. Shorter distance translates into less fuel consumption and less flight time. An aircraft needs to fly from 30° north 90° east to 30° north 90° west. There are two route options for this flight. You can either fly via great circle track denoted by the green line, or via ram line track indicated by the red line. Great circle track distance is 7,200 nautical miles, whereas the ram line track distance is 9,353 nautical miles. Imagine if you are the shareholder of an airline company, which route do you want the pilot to choose? Obviously, the great circle route. However, flying on a great circle track comes with its own challenges. On the screen is an animation showing the changes of true direction while flying on a great circle at 30° north latitude. Observe the rate of direction change. And now, animation showing the changes of true direction while flying on a great circle at 70° north latitude. If we compare the two situations, we can see that the rate of direction change is higher as the latitude increases. Therefore, it is humanly impossible to fly on great circle track at high latitude manually. Furthermore, the horizontal component of the Earth's magnetic field reduces as latitude increases, reducing the accuracy of the magnetic compass. At high latitude, the horizontal component of the Earth's magnetic field may reduce to below 6 microtesla, which make the magnetic compass useless. Adding to the problem, variation is changing rapidly, especially in northern Canada as shown on the screen, making the use of magnetic compass impractical at high latitude. Directional gyro indicator was introduced to solve the problem of magnetic compass at high latitude. However, due to gyro rigidity, the directional gyro indicator tends to constantly point toward the same point in space, which causes the problem of apparent wander and transport wander. Every problem creates opportunities. By overlaying grids based on a reference meridian, we can align the gyro with the grid instead of the local meridian. When the aircraft fly, the direction will not be changing because the gyro will always point toward grid north. By applying grid, it solves the problem of convergence while flying on a great circle track and the issues of magnetic compass at high latitude. A point that needs to be remembered: grid track is always constant along a great circle track. Section 2. Grid construction. On the screen is a polar stereographic map. Grid is usually overlaid over polar stereographic and Lambert conformal map. I will use a portion of the polar stereographic map to explain grid construction. The direction of true north is toward the center of the map, as shown by the red line. To construct a grid, we first need to choose a datum meridian. Datum meridian is also called a reference meridian. Usually, longitude 0 degree or 180 degree is used. However, for American map, longitude 60 degree west is also taken as datum meridian. At the time this video is recorded, all grid navigation questions in the database refer to either prime meridian or anti-meridian as the datum meridian. For this section, I will choose longitude 0 degree or prime meridian as the reference meridian. The direction of grid north is the same as the datum meridian true north. Other grid line is drawn parallel to datum meridian with equidistant interval. Everywhere on the chart, the direction of grid north is toward the top of the screen. By the way, don't forget to subscribe and click on the bell icon to get notified when I publish a new content. Section 3. Grid Convergence. As compass and magnetic datum, grid datum also have the angular value between it and another direction datum. The angular difference between grid north and true north is known as convergence or convergency. Similar to deviation and variation, the convergency value is either east or west. When true north is toward the east of grid north, the convergence is east, and when true north is toward the west of grid north, the convergence is west. An aircraft flies on 110 degrees grid track. True north is to the west of grid north with convergency of 20 degree west. True track is measured clockwise from true north. Thus, true track is 130 degrees. Another aircraft flies on 110 degrees grid track. This time, true north is to the east of grid north with convergency of 20 degrees east. True track is measured clockwise from true north. Therefore, true track is 090 degrees. In the first situation, we have convergence west. True track has a larger value than grid track. Whereas in the second situation, when we have convergence east, true track has a smaller value than grid track. Thus, we can derive a rule. Convergence west, true best. Convergence east, true least. East or west convergence. On the screen is a globe laid with grid. Prime meridian acts as the datum meridian. In the northern hemisphere, to the west of datum meridian, longitude line which denotes the direction of true north is to the east of grid north. Therefore, west of datum meridian in the northern hemisphere, convergency is east. In the northern hemisphere, east of datum meridian, true north is west of grid north. East of datum meridian in the northern hemisphere, convergency is west. In the southern hemisphere, east of datum meridian, true north is east of grid north. East of datum meridian in the southern hemisphere, convergency is east. And in the southern hemisphere, west of datum meridian, true north is west of grid north. West of datum meridian in the southern hemisphere, convergency is west. This situation can be simplified using EWWE diagram as shown on the screen. The top half of the diagram represents northern hemisphere. The bottom half of the diagram represents southern hemisphere. The middle vertical line represents the datum or reference meridian. To demonstrate the usage of this diagram, I will use two examples. Example 1. North polar stereographic. Datum meridian is the prime meridian, position 60 degree east. This middle line is the datum meridian. Next, locate the position in relation to datum meridian. When prime meridian is in the middle of the map, 60 degree east is to the right of prime meridian as shown on the map. Therefore, 60 degree east longitude is here. Since we are in the northern hemisphere, convergence is west. Thus, convergence is 60 degrees west. Example 2. South polar stereographic. Datum meridian is the anti-meridian, position 80 degrees east. This middle line is the datum meridian, in this case anti-meridian. Next, locate the position in relation to datum meridian. When anti-meridian is at the center, 80 degree east is to the left of anti-meridian as shown on the map. Therefore, 80 degree east longitude is here. Since we are in the southern hemisphere, convergence is west. Thus, convergence is 80 degrees west. Amount of convergence. In aviation, grid is overlaid onto polar stereographic and Lambert conformal chart. Amount of convergence for polar stereographic chart is convergence equal to change of longitude. For Lambert conformal chart, convergence equals change of longitude multiplied by sine parallel of origin, or convergence equal change of longitude multiplied by constant of cone. At the time this video is recorded, there is no grid navigation question regarding Lambert conformal chart in the database. CDMVT plus CG. Because grid north is a type of direction datum, the procedure to convert grid direction to true direction is similar to the method of converting between direction datum that was explained in part 2 of this video series. We just need to add 2 more columns to the CDMVT table. The 2 additional columns are titled C for convergent and G for grid direction. Convergent east is positive and convergent west is negative. If you are not familiar with this table and have not watched the second part of this video series, you should watch the second video first. And afterward, you can come back here and continue watching the rest of this video. The link to the video is available in the description and at the top right hand corner of this video. To demonstrate the usage of this additional column, I will use 2 examples. Example 1. Track 300 degrees true. Grid convergence 45 degree east. Find grid track. We will only need the last 3 columns of the table to answer this question. Next, insert the table with the appropriate value. 45 degrees east is equal to plus 45. Since we are calculating in the same direction as the general calculation direction, grid track is equal to 300 plus 45. Grid track is 345 degrees. Example 2. Track 0 to 0 degrees grid. Grid convergence 60 degree west. Find true track. Insert the table with the appropriate value. 60 degree west is equal to minus 60. Since we are calculating in the opposite direction against the general calculation direction, instead of true track equal to 0 to 0 minus 60, it becomes 0 to 0 plus 60. Therefore, true track is 080 degrees. Grevation. Grevation is a method to directly convert from magnetic direction into grid direction. Grevation is simply convergence plus variation. Isograph is defined as line joining places of equal grevation. Using the standard procedure to convert from compass direction to grid direction, you need 3 steps. By calculating grevation, pilot using magnetic compass can convert from compass heading to grid heading in just 2 steps instead of 3 steps. This example will demonstrate how to calculate grevation. Convergence 18 degree west plus variation 5 degree east, grevation equal 13 degrees west. Treat the difference between east and west like positive and negative in standard math calculation. Convergence 12 degree east plus variation 4 degree east, grevation equal 16 degree east. Convergence 13 degree east plus variation 4 degree west, grevation equals 9 degree east. Section 4. Drawing grid problem. This method can only be used for grid problem on polar stereographic chart. This method can also be used to solve polar stereographic grid circle question. The drawing convention aims to ensure that the grid nose is pointing toward the top of the paper. Even though it is not compulsory to use a drawing convention, to avoid confusion and for organization purposes, I strongly suggest all grid navigation problems are drawn using the drawing convention. Drawing convention. On the screen is the summary of the grid problem drawing convention. You can download the PDF version of this summary. The link is available in the description. Don't worry, it is free. Now, let's look at how the drawing convention constructed. Suppose you were given North Polar Stereographic chart with 0 degree longitude as the datum meridian. The first step is to turn the globe until you are facing the datum meridian. Next, turn the globe so that you face the pole. In this case, since we were given the North Polar chart, we need to turn the globe downward to face the North Pole. Observe the position of prime meridian, anti-meridian, 90 degree east and 90 degree west. The drawing convention is based on the relative position of these 4 points. Let's take a look at another example. This time, we were given South Polar Stereographic chart, datum meridian 180 degrees. Turn the globe to face 180 degrees longitude. Rotate the globe to face South Pole. The drawing convention follows the relative position of prime meridian, anti-meridian, 90 degree east and 90 degree west. If you do not have a globe laying around in your house, you can use any spherical object in your home to help you imagine the situation. Or you can download this 3D model which I created to help you understand the drawing convention. Link for download is available in the description. Measuring direction. This diagram represents the North Polar chart with prime meridian as the datum meridian. The graphic shown will represent aircraft heading since we will measure toward the direction where the aircraft is pointing. However, I will refer the situation as direction to emphasize that this technique can also be used for another type of direction line such as track and course. On this diagram, the center of the circle is the geographical North Pole. Therefore, the direction of true north is toward the center of the chart as denoted by the red triangles. For this aircraft, the true direction is 360. This chart is drawn using the drawing convention. Grid north at any position on the chart is pointing toward the top of the screen. Grid direction is 360. Here is another aircraft on the same chart in a different position. The direction of true north is toward the center of the diagram as shown by the red arrow. True direction is measured clockwise from true north toward the direction line. True direction is 090. Grid north is pointed toward the top of the chart as shown by the blue arrow. Grid direction is 360. Here is another aircraft on the same chart in another position. The red arrow denotes the direction of true north. True direction needs to be measured from true north clockwise toward the aircraft direction line. True direction is 180. As mentioned before, grid north always pointed toward the top of the screen. Grid direction is the angle between grid north and aircraft direction line measured clockwise. Grid direction is 270. On the screen is a diagram representing South Polar Stereographic Chart with prime meridian act as datum meridian. The center of the circle represents the geographical South Pole. Therefore, the direction of true north is away from the center as denoted by the red triangle. At the location of the aircraft on the diagram, true north direction is denoted by the red arrow. The true direction is measured clockwise from true north toward aircraft direction line. True direction is 270. Since this diagram is constructed using the drawing convention, grid north will always point toward the top of the screen. Grid direction is 360. Let's take a look at one final example. For this aircraft, direction of true north denoted by the red arrow. True direction is 180. The blue arrows show grid north. Grid direction is 090. Section 5. Grid through conversion. There are 4 methods to convert between grid and true direction. Mnemonic, CDMVT plus CG table, accurate drawing, and sketching. For examination preparation, you just need to choose one method that suits you the most. I will use this example to explain all 4 methods. North Polar Stereographic with Greenwich Meridian as the reference meridian. Aircraft is at 70 degree north, 110 degree west with heading of 100 degree through. Find grid heading. Mnemonic. The mnemonic that we need to use is convergent west, true best, convergent east, true least. The first step is to find convergent. To find convergent, we will use the EWWE diagram. The center vertical line represents reference meridian. For this example, 0 degree. Next, we need to locate the position of 110 degrees west in relation to 0 degree longitude. By referring to the map on the screen, 110 degrees west is to the left of the prime meridian. Since the example stated that this is a north polar chart, our position will be in the top left region. The convergent is east. For a polar stereographic chart, the value of convergence equal to change of longitude. Thus, convergence equals 110 degree east. The second step is to use the mnemonic. Since the convergent value is east, convergence is through list. This mnemonic can be rewritten as through heading is equal to grid heading minus convergent. It is minus because through heading is less than grid heading. Next, we need to rearrange the formula. Grid heading equal through heading plus convergent. Insert the appropriate value. Grid heading equals 100 plus 110. Grid heading equals 210. CDMVT plus CG table. For this technique, the first step is to find convergency. Method of finding convergency is the same as the previous method, so I will not repeat it. Next, insert the appropriate value into the table. 110 degree east is equal to plus 110. Since we are calculating in the same direction as the general calculation direction, grid direction equals 100 plus 110, 210. Grid heading equal 210. Accurate drawing. The first step is to draw the diagram by using the drawing convention. Draw a circle. This circle represents latitude 70 degree north. Since this is a north polar stratigraphic chart, the center of the circle is the geographical north pole. Therefore, the direction of true north is toward the center of the diagram. If we want grid north pointing toward the top of the screen, our reference meridian needs to be drawn at 6 o'clock position. Opposite to the prime meridian is the anti-meridian 180 degrees. Since this example uses prime meridian as the reference meridian, longitude 90 degree east is on the right and longitude 90 degree west is on the left. Next step is to draw longitude 110 degrees west. Align your protractor with the center of the circle. Rotate the protractor so that 0 degree on the protractor is aligned to 0 degree longitude. Measure 110 from 0 degree longitude on the western side of the diagram. Draw the longitude line. The intersection between the circle and longitude line that we just draw is the position of the aircraft. From this position, true north is toward the center of the diagram as indicated by the red arrow. The next step is to draw through heading. To draw through heading, you need to align your protractor with the position of the aircraft. Align north of the protractor toward the center of the circle. Measure 100 degrees clockwise from true north or the longitude line. Draw the direction line. Next step, measure the grid heading. Since we draw this diagram in accordance with the drawing convention, the direction of grid north is always pointing towards the top of the screen, anywhere in the diagram, shown by the blue arrow. Align your protractor with aircraft position. Align protractor north with grid north. Grid heading is the angle measured clockwise between grid north toward where the aircraft is pointing. Read the answer. Grid heading equal 210 degrees. Sketching. To use this technique, you need to have a basic understanding of circle theorem. Before we start, I need to warn everybody that my handwriting and sketching is awfully bad, so please bear with me. The first step is to draw a diagram using the drawing convention. Draw a shape that looks like a circle. Mark the position of prime meridian, anti-meridian, 90° east and 90° west. Draw the position of 110 degrees longitude. It is 20 degrees after 90 west. It is roughly here. Next, draw through heading. Tangent to the circle is 90 degrees. 100 degrees is roughly here. Value of this angle is 100 degrees. Next step is to find grid heading. Grid nose is pointing toward the top of the screen. Grid heading is the angle between grid nose and the true heading line. This angle can be divided into two segments. First segment are between these two lines. It is 100 degrees. And the second segment is between these two lines. We do not know the value of this angle. I name it as X. Now we need to use circle theorem. If we extend this line, the value of this angle is also X. So does this angle. The value of the last angle is the same as the angle between 0 degree longitude and 110 degrees west longitude. It is 110 degrees. Thus, this angle is also 110 degrees and so do this angle. Therefore, grid heading equals 110 degrees plus 100 degrees equals 210 degrees. What do you think of this video? Please let me know in the comment section below. And if you find the video beneficial, please like it and share with others. By doing so, you will help other people to find the video. If you want to learn more about ATPL or other aviation related stuff, subscribe now by clicking on the round subscribe icon. Please check out my other video by clicking on the rectangular box. Thank you so much for watching. I'll see you next time.